Okay, thank you again. I've been in this IT business for a long time, and any IT system that are good are supposed to have glitches. They are very complex systems. So, by no doubt, the Exceed portal is a very good system, and thus will have glitches, unfortunately. So again, welcome. The purpose of today's keynote is to just give you a little flavor of the machine we're building. I'll give you a flavor of our center, and also give you a flavor of some of the more recent AI and big data activity work we are doing at our center. So first of all, oops, oh, it's not changing, okay. So again, all IT systems have glitches. It's all black. Oh yeah, okay. So we are Riken R-CCS, and Riken itself is the one of the two biggest national labs in Japan. Basically do lots of science and also some engineering technology. And Riken R-CCS is one of the 15 research centers we have at Riken. And I'm the director. I've been appointed the director there in April. I'm still a professor at Tokyo Institute of Technology, but throughout my career, I've been doing HPC, building machines, writing software, inventing algorithms, and so forth. Our goal at our center, our CCS in particular, is to basically study computing, because we are a center of computing. So thus we study computing. But what does it mean to study computing, especially in the high end? Well, so our motto, or our slogan, is science of computing, by computing, and for computing, which is, if you have an American citizenship, this is something you're maybe synonymous to. Now, a famous quote by, a little bit of a twist on a quote by one of your very famous presidents. The U.S. has lots of famous presidents, a recent one too. And so what do we mean by science of computing? Well, we study computing as the target, as a target of a scientific study. So this is in other words, this is computer science, but I don't like the term computer science because when you say computer science, people think you're just hacking machines and fixing Windows bugs all the time. Right. No, it's really, science of computing is really studying what computing is in a scientific fashion. And thus we study software, programming, algorithms, new architectures, analytics, artificial intelligence, anything that's related to computing and on the high end. And science by computing is what will give us, this science of computing will give us tremendous computing power. And how do we use that power to drive other branches of science? So there are many branches of science and also societal, those of societal importance that are now rely on the computing technologies, especially areas that are of high concern to society, like climate, environment, life science, disaster, advanced manufacturing, and energy, and so forth. And then there's a science for computing, those types of sciences that help advance computing, the other disciplines like materials, new semiconductors, and so forth. So together, there will be a synergy between these three and drive the science forward regarding computing. So that's our motto. And we have, in order to study these areas, my pointer's not working, so I have to go here. Okay, so we have 19 research teams. I'm sorry, it's in Japanese. I couldn't find the English one. The brochure, you have a brochure inside you that describes each of the teams. So we have 19 teams in total. And we are actively soliciting interns and postdocs and scientists. So if you are a grad student, if you like this summer school, you want to spend more time here with any of the research teams, got our brochure. They make their internship positions open, or if you're going to get a PhD real soon, there are postdoc positions. And then if you're already a postdoc, we have research, either postdocs or even full-time research positions available. And we're always seeking very good international talents. And in fact, it's my personal agenda to really step up this recruiting interns, postdocs, and also full-time researchers. So again, if you're interested, and if you're talented, you're very, very welcome to join us. Okay? Now, so research is one of our major facets. So like I said, we have many people doing research. And also we collaborate a lot with universities, industry, both domestic and also international. And also labs like, NSF centers, DOE centers, and so forth. And also, European centers. But also, we are the tier 1 center of what's called HPCI. Now, HPCI it stands for High Performance Computing Infrastructure. So, not a very inventive name, but I didn't come up with this stuff. It's not cool like Exceed, I'm sorry, or Praise. But, this spells out what it is. In fact, we are the tier 1 center where we host a K computer, and I've been told that you'll have a tour of the K computer on Friday, which is our current machine, but will be decommissioned in August to make room for the Fugaku machine, which I will talk about next. But we have also 12 other resource centers and various university centers, including Tokyo Institute of Technology, where Tsubame is the machine I have been building there for some time, a series of Tsubame machines. And also recently, AIST, which is another big national lab, they have a new big AI machine called ABCI, which I had also built. But collectively, we formed this alliance of supercomputing centers, and we also have a common storage by which people can, ship data over, compute, and ship the data back. So despite the fact that the machine will be decommissioned, there'll be a little bit of a blank period. Overall, the national infrastructure will cover for the missing cycles for the time being until we launch Fugaku. But overall, this heterogeneous configuration that's linked by 400 gigabit network at the trunk, and hopefully will be upgraded to terabit soon, gives us this holistic distributed supercomputing infrastructure in production, much like Exceed, and also much like Praise. So, but we're tier 1. Everybody else is tier 2. So unlike Exceed and Praise, where things are a little bit flatter, we have a hierarchical structure in that regard. Okay, so that's so we are responsible for running the big K computer and Fugaku. Now, so what's Fugaku? Well, Fugaku will be our next big machine, and the Fugaku means this, and probably people know what this is, right? There have been zillion shots on the internet, photos of good ones, the bad ones of our pride mountain, Mount Fuji. Fugaku actually means Mount Fuji. It's a different word for Mount Fuji. Usually in Japanese you call it Fujisan, meaning Mount Fuji, but Fugaku also means Mount Fuji. It's a more classic word. And why? So we regard Mount Fuji as the ideal of supercomputing, because on one hand it has a very high peak. It's the highest mountain in Japan. It stands out, as a lone statue. So it's the acceleration of large-scale applications. So it does very well in terms of the capability. But also it has a very, very broad base. If you've ever been how many people have been to Mount Fuji? Oh wow. Okay. How many people have climbed Mount Fuji? Oh wow. I'm envious. I never have. So yeah, must have been a great experience. Yeah. So but you never do it in winter. If you did it in winter, it can get freezing as in Antarctic, so people die actually. So don't ever. They close the mountain. Don't ever climb it in winter. Summer is great. So it has a very broad base. So broad base meaning both in terms of application and capacity. So, so we don't want these big machines to be like, in Tokyo there's a thing called a Tokyo Tower. There's also a new tower, which is like a needle. And these towers are very tall, but they are very narrow in their base. So, but we don't want that. We want these machines to be accommodating. We want broad applications to run on these machines, not just traditional simulation science, but also data science, artificial intelligence. We also want very broad user base. We want academia, we want industry. We also want cloud adoption. That is, our technologies that are used to build these machines being the bleeding edge technologies. We want the technologies developed, developing these machines, running these machines, and also all the software and applications to permeate to the cloud. So we want this kind of broadness and also very high peak at the same time. And the Mount Fuji is a perfect signature to represent that kind of idealism. So, of course, Fugaku as a machine is not a mountain. It's a machine, it's a supercomputer. So what does it look like? Well, so we believe that Fugaku, even compared to the existing K computer, which is the photo you see over there, it's a game-changing machine in the supercomputing arena. So on one hand, it inherits a lot of the properties of K. All the codes running on K are supposed to run, by and large, automatically on the Fugaku with just a matter of recompilation. Has a very similar architecture, has a it's bigger, but the network topology is the same. And of course, Fujitsu, our partner company, will supply the compatible compilers and libraries. The only difference there is on some of the apps, Fugaku will be 100 times faster than K, which is a good thing. Yeah. Anybody who says, I'll run your code 100 times faster, great. Okay. But that's not all. But we believe that the technologies that have been developed to achieve that goal is really a game changer, and this is very different from K. So in the K, the processor that was developed, the Spark FX8, to be I'm very honest here, was okay. The machine was good, but the processor, the chip, was sort of okay, but not fantastic. So I did a lot of benchmarking. So when Fugaku was starting to be developed, the first thing we did was to benchmark the K processors, the CPU, to Intel or AMD, other mainstream processors. And the result was the chips weren't bad. So in some cases they were faster than Intel a little bit, but in other cases they were not. And by and large, they seem to be pretty much on par, which is okay again, but then you don't have any compelling reason to, buy the chip or buy the machine, because why would you just get an Intel? That's it. And you're part of the Intel ecosystem, the x86 ecosystem. Whereas Fugaku is very different. So the chip that was developed this time is really outstanding. Outstanding in terms of performance. So we see on some of the benchmark, we see almost an order of magnitude speed up over existing mainstream Intel processors and HPC workloads. It's also very green. We see power efficiency figures way above standard CPUs. So it'll be the most power efficient CPU, general purpose CPU. It'll match or even exceed some of the current GPU power efficiencies. But even so, these are very good performance metrics. It's an ARM processor. It's an ARM's, we didn't buy the IP from ARM. We only bought what's called the architectural license, meaning that we can build a processor running ARM code. All the architectural underpinnings were done by Fujitsu and us. But still, it's an ARM processor. It's a pinnacle. That's a very top tip of this ARM ecosystem. But ARM sells something like 21 billion chips per year. Everything from your smartphones, you have an ARM chip probably in your pocket. I have two in my pocket too. And also, it's in your car, it's in your fridge, everywhere. So, but it's a pinnacle. So there's a very vast ARM ecosystem. And also, we've been able to add some features which will be relevant to the new breed of applications, including AI. And that's very important for driving what we call in Japan as Society 5.0, which is something we copied the Germans saying Industrial 4.0. Okay, so let's make it a society, broaden it, and let's increase the number one. But really, it's the HPC becoming mainstream, a driver for the societal improvement, is something that we're aiming. And for that, we need both generality and performance and support for new types of applications. So, I don't have really that much time to go into details of the architecture. I'll pass by very fast. I'll make the slides available later. If you're interested, you can read the details. The part where I really swing by very fast. But just to give you a little overview of the numbers, if you're interested, if you're more of a systems, science of computing, systems-y type of person, well, the reason we were able to achieve this performance was because the chip was HPC optimized. The chip had been built with HPC workloads, just the HPC workloads in mind, not serving the web, for example. So if you're serving the web, it's better to buy Intel or AMD, because they've been optimized for that. But this chip has been completely designed, ground up, supporting HPC. And as such, it has a very, very high memory bandwidth. It has a 1 terabyte per second memory bandwidth supplied by, if you look at the photo, this is a real chip. The CPU core is here, and then you see the high bandwidth memory, just like the high-end GPUs. It has a built-in network. It's called TofuD, which gives us a 400 gigabit per second network injection bandwidth, which is every chip is like an internet backbone, essentially. It has very high SVE, what's called scaled vector extension, and very high performance due to SVE scale, which was developed by ARM jointly with other companies like Fujitsu and Cray. And also, as part of SVE, has various AI support, like the reduced precision mathematics, and as I'll tell you later, support for convolutional operators and so forth. But still, it's a general purpose CPU. It's an ARM processor, so it runs Linux. It just boots RHEL out of the box. It should. I've heard it runs Windows. In fact, runs Word. Probably the fastest Word. If you build a workstation out of it, you can run lots of Word instances, and probably the fastest Word processor in the world. Okay, so that's the chip. And then what we do is as parallel computers go, massively parallel supercomputers go, we assemble these into a massive machine, just like big supercomputers and like big clouds. So we'll have more than 150,000 nodes, and this will be the largest node count ever for a supercomputer, surpassing the Livermore Sequoia, which had 130,000 in the past in Luigi. What's most important, so it's not so much the flops. What's important is the memory bandwidth. So we'll have more than 150 petabytes per second memory bandwidth, which is 7 times the capacity of the fastest machine in the world right now, which is Oak Ridge Summit. And as you know, if you have programmed in these HPC codes, you'll find a lot of the methods are memory bound and not flops bound, like conjugate gradient, any of the stencil codes, and so forth. So memory is your limiter and performance limiter, and we have plenty of it. Also have very high network injection bandwidth, 50 to 60 petabits per second. And if you put this in context, this is 10 times the global IDC traffic, intra-IDC traffic. All the Googles and Amazons, all the data centers, their internal traffic, there are hundreds of those data centers all aggregated, but their data bandwidth, average data bandwidth is 1/10 of the network's capabilities here. We have tens of petabytes of NVMe storage, have 10,000 endpoint I/O. So in essence, this will be one of the first exascale machine. Exascale meaning this is sort of a machine, and the performance that will be enabled by the machine is something that will be that some people have expected out of an exascale machine. So, and this will likely be launched in about a year. So this is what the diode photo looks like, and just like a modern architecture, has a whole bunch of cores. In fact, it has 52 cores, as I'll tell you. But each core is a high-performance ARM core. So we're almost about a year away from deployment, and by first quarter 2021, hopefully the operation will start. And then, of course, as a research lab, we're already starting to think about the next one, which is a challenge. So how do we achieve this? And this is where, the idealism of this center really is reflected, whereby we say, well, there needs to be a synergy collaboration. In fact, when the whole exascale activity started around the globe, in Europe and US and also in Japan and China, especially in those, when we started these activities back in early 2010s, the thought was, because of the difficulty in achieving these performances and scale, what was really needed was the co-design. Co-design meaning we have the applications, the high-end applications, then we have the computer science and their technologies, and they really need to work in synergy. Okay, so it's not as much as you think these things are designed in sync, maybe at some level, but really this holistic design of the machine versus the applications, it's really difficult to conduct. So, like I said, as much as I respect Intel, I bought lots of Intel chips in my career. But Intel, at the end of the day, they optimize their chips for cloud workloads. Of course, they have some elements of HPC, but that's not the only target they have. And it's not like they use all these high-end applications as their benchmarks. So at Riken, and also partnering with other institutions in Japan, University of Tokyo, climate labs, genomic labs, and so forth. There's been like 9 target apps, target areas, and target application areas, and we came up with 9 target applications. And the goal was to achieve up to 100 times speed up over the K computer, up to. Well, on the average, it'll be lower. But the goal was to come up with the machine that will accelerate these HPC workloads, and that's our primary target. So, it was a very long design process. Everything kind of started in 2011, and then there were stages of various projects. There were like feasibility study. I was leading one of the application teams. Application effort, there were architecture teams, and then 2014, the K became what became post-K. Now Fugaku became an official project, and there's been lots of development going on. But how do we do the code design? And this is very important. So what we have, because there are lots of architecture parameters that need to be decided. Because at the end of the day, when designing computer architecture, of course there are lots of innovations, but also it's an engineering effort where we have to basically balance everything, because we have finite transistor budget and we have finite power budget. So how do we come up with an architecture, with these constraints, limit and budget, and how do we, maximize, squeeze every bit of performances out of the architectures with these target applications in mind. So we had 9, like I said, there were 9 areas, from medicine to climate to materials to manufacturing and so forth. And of course, these teams have been, just like DOE co-centers, they've been doing their own work, basically doing very broad work regarding their science. But what you asked them to do was to pick one app that's representative of their domain. So these are the 9 apps: molecular dynamics, genomics, earthquake, climate, first principle molecular orbital chemistry, structures, RSDF, DFT, also conjugate gradient type, and also adaptive mesh refinement, and also things like QCD. So these are the 9 applications, and then we did a whole bunch of stuff. Running this on our proxy machine, which was a previous generation machine to Fugaku, the FX100, which is a generation after the K. But look, there are lots of architectural commonalities there. So we could do good tuning estimation of these using the proxy architecture. We also developed a simulator, and we also had an optimization team that analyzed these codes and looked at the bottlenecks and what the architecture implications are, blah, blah, blah.